Dear students, now we are going to see a problem in radiation cells, especially in the two plates in between we insert a radiation cell. How much heat transfer that may be reduced in the presence of radiation cell. So here the first case, note that this is the first one. So between the these are two plates. In between the two plates, we are going to insert one radiation cell. That radiation cell, this is the one radiation cell we have inserted. So by inserting radiation cell, how much heat transfer is reduced? That is the thing we are going to study, solve here. So first we move the problem. So the two large parallel plates with emissivities of 0. Say that is 0.3 and 0.5 respectively have exchanged the heat by radiations. The planes are 800 degrees Celsius and 300 degrees Celsius. So listen, first we solve the problem. So she have a two plates. This is a plate number one. Uh, this is a plate number one, and this is a plate number two. Plate number two. The plate number one, they're having a temperature of 800 degrees Celsius, and plate number two having a temperature of 300 degrees Celsius. Then this having emissivity, the plate having emissivity that is called is epsilon 1 is equal to 0.3 and epsilon 2 is equal to 0.5. So this is the first case. So in the first case, we are going to find the what is the net radiated heat energy between these two plates. So first we solve the problem number one for subdivision one. So for finding a heat transfer between the two plates, we have a formula that is called as a Q1 to 2 between the plates 1 and 2. We have a formula so which is equal to epsilon bar sigma A into that is a T1 power 4 minus T to the power 4. So this formula is derived from the Stephen Boltzmann's law. So where the Stephen Boltzmann that is a Q is equal to epsilon into that is sigma A into that is a T1 power 4 minus T to the power 4. Here we are using a two heat exchange between the two plates which are having a two different emissivity. That's why we are using epsilon bar. So in that formula, you write the formula for epsilon bar. So what is epsilon bar? Here epsilon bar which is equal to that is 1 divided by this is standard formula 1 divided by there is epsilon 1 plus 1 by epsilon 2 minus 1. So this is a standard formula to find the epsilon bar. So we substitute the epsilon bar in the equation that is called as a q1 to 2. So q1 to 2 is equal to that is a sigma then a then t1 to the power 4 minus t to the power of 4 divided by that is a 1 by that is epsilon 1 plus 1 divided by epsilon 2 minus 1. Here also the question asked is there is net radiant heat exchange per square meter of the plate. So we take an area here. There is a Q1 to 2 divided by A, so which is equal to epsilon. You already know that is called the Stephen Boltzmann constant. So 5.600 10 to the power minus 8. Then watt per meter square, that is a Kelvin power 4. In terms of temperature, the temperature T1 and T2 should be written in terms of Kelvin only, not to use in the temperature. So 800 plus 273. Here we can written as that is equal to 1073 Kelvin. So this is the T1. Similarly for T2, we can write in the Kelvin. So T2 is equal to 300 plus 273. So T2 is equal to 573 Kelvin. So better we substitute temperature in Kelvin for this equation. So here there is a 1073 whole power 4 minus what 573 whole power 4 divided by 1 by epsilon 1. Epsilon 1 is equal to 0.3, that is 0.3 plus 1 divided by 0.5 minus 1. So after substituting the values in the above equation, finally we can get the heat transfer Q1 to 2 divided by A. That is per unit area we can get the value which is equal to that is equal to 15.88 kilowatt per meter square. So this is a case one. Case one we find. Then we move to the second case. So in the second case, here one radiation cell that is inserted in between these two places. Note that a radiation cell having emissivity of 0.064 is placed between them. Here we are inserting one radiation cell that sealed, that is a radiation cell that sealed having emissivity that is you can written that there is epsilon 3. The seal number is 3 which is equal to 0.06. We don't know the temperature of this plate. radiation, there is a, you don't know temperature of this cell. So by inserting the radiation cell between the two plates 1 and 2, how much percentage of radiation heat exchange is reduced? So how much percentage reduction in the radiation heat exchange and temperature of the cell? So in the second part we are going to find the two things. One is the how much percent of radiation is reduced, then temperature of the cell. So before we finding the percentage reduction in radiation of the heat exchange, first we find the temperature, then only move to the first part, that is a reduction in radiation. Okay. So otherwise, we can find the reduction in radiation. So which percentage of reduction is equal to percentage of reduction is equal to, first there is a Q, that is a without, so without seal, minus Q with seal divided by, so that is called as a Q without. So this is the formula to find the percentage reduction in radiation by inserting the field. Similarly, it can be written as Q without cell, we can written as that is a Q122, because this case there is called as the without cell. So Q122 minus in terms of with cell. With cell means it can be transferred from 1 to 3. So that is a Q123 divided by, that is a Q, sorry, that is a Q122 into 100. Okay. So Q122 into 100. So for that we are going to find Q122. So Q123. How we can find the Q123? We are finding the, this called as a Q123. So for finding a Q123, we have an equation, because the plate is between the 1, that is the plate is for the 1 and the shield is 3. For 1 to 3, we can write as epsilon bar, again epsilon bar sigma A T1 to the power of 4 minus T3 to the power of 4. Here we can written that is a Q123 divided by A, that is epsilon bar into sigma, that is a T1 to the power of 4 minus T3 to the power of 4, which can be again written as that is sigma into T1 to the power of 4 minus T3 to the power of 4 divided by epsilon bar, we can be written as 1 divided by epsilon 1 plus 1 divided by epsilon 3 minus 1. Here what is the difference between the previous one, this one, please note that. So in this one we can written that is called as epsilon 2, but here you can written what is that is called as epsilon 3. So in the second case, you note that the here we know the some terms. So sigma already you know, T1 you already know, epsilon 1, epsilon 3, everything, but it doesn't know T3. It doesn't know T3. First we know the T3. T3 is nothing but the temperature of the seal. If you know T3, then only you are going to calculate the, this is a Q13123, then you can substitute the Q123 here. So how we find the T3? For finding T3, we move to the another one correlation. Listen. So Q, for similarly for Q123, we can find a Q322. Find Q, that is a 322. How we can write the Q322? Q322 is equal to epsilon bar, then sigma, sorry, there is not written here. So there's a Q322 is equal to epsilon bar sigma A, that is a T3 to the power of 4 minus T2 to the power of 4. Here there is a Q323 divided by A, which is equal to, then sigma is not written clearly. There is a T3 to the power of 4 minus T to the power of 4 divided by, you can sigma symbol here, divided by 1 divided by, that is epsilon 3 plus 1 divided by, that is epsilon 2 minus 1. So this is the another term, find Q123 divided by A. Here it is the Q123 divided by A. So what is the reason for finding Q123 and Q322? So at some condition, note that Q Q1 to 2, that is a Q13T divided by A, which is equal to Q322 divided by A. So for what the reason we are going to find, we are going to equate the Q, because this is a plate number 1, this is a plate number 2, in between we are having a radiation shield, so this is called as a 3. How we can equate this 1 to 3 is equal to 3 to 2 means, here the radiation shield does not deliver any heat or remove any heat from the system. You consider this is a system, so from outside this is a system. So in the system it does not deliver the heat or remove the heat from the deliver or remove the heat from the system. So we can equate these terms, then Q1 to 3 is equal to Q3 to 2. So Q1 to 3 we already find it. So this is the equation, this is the equation. Here we can be written as, so which is equal to sigma A, here T1 to the power of 4 minus T to the power of 4 divided by, that is a 1 divided by epsilon 1 plus 1 divided by epsilon 3 minus 1 equal to sigma A is a 3 t to the power of 4 minus t2 to the power of 4 divided by 1 by epsilon 2, sorry, epsilon 3 plus 1 by epsilon 2 minus 1. So this is a thing we are going to equate these two terms. So this is the that is a q 1 2 3, this is the what, that is a q 3 to 2. So it's by A, you can, because it is unitary, you can put A or not, it doesn't matter. So in the above equation, we strike out the common term, sigma is a constant, so A is a constant, sigma A is a constant. So then remaining terms you are going to write here. That is equal to T1 to the power of 4, T3 to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 3 minus 1 is equal to T3 to the power of 4 minus T2 to the power of 4 divided by 1 by epsilon 3 plus 1 by epsilon 2 minus 1. So we substitute the values here. Already know T1, so T1 is equal to 1073, this is equal to 573. So 1073 whole power 4 minus T3 whole power 4 divided by 1 by epsilon 1. So here epsilon 1 is equal to 0.3, it is a 0.5. Here it is the 0.3 and it is a 0.5. Then epsilon 3, which is equal to 0.06. So 1 divided by 0.3 plus 1 divided by 0.06 minus 1. So equal to, that is a T3 doesn't know, T3 power 4 divided by T4, T2, which is equal to 573 Kelvin. Then for 4 divided by 1 divided by epsilon 0.06, that is epsilon 3, and epsilon 2, that is 1 divided by 0.5 minus 1. So in the above equation, we know all the terms except T3. By substituting the values, we can get the T3. So that may be around, that is a 911 Kelvin. We find that is a T3. So here one term is given in the question. Note that so net radiant heat exchange and temperature. The temperature of seal we can find, that is a T3. So T3 is equal to, that is equal to 911 Kelvin. We find the temperature. Then how we can get the percentage reduction? So for percentage we need a Q123. Then substitute the temperature value in the Q123. Listen. So Q123 is equal to, already know, that is a sigma Q123 divided by A, sigma T1 power 4 minus T3 divided by 4 divided by 1 by epsilon 1 plus 1 divided by epsilon 3 minus 1. Here sigma you already know, 5.6 to the power of minus 8. So T1, that is 1073 whole power 4 minus 911 whole power 4 divided by 1 divided by 0.5 plus 1 divided by 0.06 minus 1. So after the substituting value, we get the Q123 divided by A, say, which may be equal to, that is equal to 1 point, the value may be nearer to 1.89 kilowatt per meter square, because we are considering unit area, so we can return this, that is called meter square. Here also written in terms of meter square. So now we substitute the how much percentage of reduction. So here the percentage of reduction can be written as, so percentage of reduction which can be calculated as there is a Q without minus Q with divided by there is a Q without into 100. So that is equal to Q, that is 122 minus Q123 divided by Q122 into 100. So Q122 already find, which is equal to 15.88. So 15.88 minus Q, that is 123, that is equal to 1.89 divided by 15.88 into 100. So after substituting the value, percentage of reduction is equal to, which is equal to almost nearer to 88 percentage. So for this problem, so without sealed, we have some 100%, assume that we can take as 100. By inserting on radiation seal, the radiation from the Q122, that is 1 to 122, that may be reduced up to, that is percentage is reduced, that is around, that is 88% is reduced. Okay, clear? Thank you.